Good afternoon, everyone, and welcome to our round of webinars focused on the inspection on the ZDZW project. Today with us, we have a new webinar entitled Digital Twins as Non-Destructive Inspection Techniques for Manufacturing Process, being offered by our colleagues from IKERLAN. So, without further delay, I will give the floor to my colleague Mayalan. Mayalan, so the floor is yours.
Thank you, Oscar. Okay, so first of all, thank you for coming. My name is Mayalen Aritortena, as Oscar said, and I'm a researcher here at IKERLAN, and I'm coming from the mechatronics department. Today, we are going to see how digital twins can be used as non-destructive inspection techniques in the context of manufacturing processes and the work that we have done in the ZDZW project. So this is the index that we are going to follow throughout the presentation. And first, I wanted to tell you a little bit about the ZDZW European project. We are coming to the end of the project this August, but it has been a 3-year project where 27 partners from 10 different countries have been participating in the development of different non-destructive inspection services. And we have been working mainly in 3 different categories of solutions: integrity, thermal, and visual. And the solution that we are going to see today comes from the integrity suite, let's say. And we have been working or demonstrating these solutions in different pilots, and we are going to focus on pilot 4 today. This is from Ereka, a Basque company that produces large-size bolts, mainly for the wind industry. So this is the case study that we are focusing in for this solution. Next, I will speak a little bit about IKERLAN also. We are a research center, a technology center with more than 50 years of history already. And the aim of IKERLAN is to develop technological solutions that we can transfer to different companies. So we are currently over 400 people working here. You can see that we have a lot of people as trainees and many doctoral theses in progress. The total income from last year was about 33 million euros, and our income is divided into main groups: transfer projects with companies, and also funded research projects from different governments. And this is the top sectors that we work, mainly transport, mobility, energy, and manufacturing could be the most important ones that we usually work with. In our specific groups, in the mechatronics technology, we have a research line where we develop different simulation models for manufacturing processes. We are currently working in induction and laser technology, and we use these 2 technologies for welding, for heat treatments like hardening, tempering. And our aim here is to develop different simulation models, and also develop some inspection techniques that we can use in combination with the simulation models. And here you can see some examples of inspection techniques that we are developing based on acoustic emissions, then some simulation models that we have developed for different manufacturing processes, such as induction, laser welding here. And we also have some testing equipment, mainly an induction test bench and a robotic laser cell. And with that, we can validate the simulation models that we develop, and also use our inspection techniques to improve them. So today we're going to focus on the induction hardening manufacturing process and or induction heat treatments, specifically hardening and tempering. And in the industry, the common failures that we can find in these types of processes is that we don't achieve a case depth that is enough for the specification. Usually when you use an induction heat treatment, you aim to have a hardened case depth, and for that you need to increase the temperature of the workpiece up to, let's say, 800 degrees Celsius, and then you have to cool it fast. And if you don't reach enough depth in this heating and cooling process, you are not able to harden the workpiece enough. So we have several problems related to that, not reaching enough depth, or not having a uniform case depth in the whole workpiece that you want to analyze. And also, if the process is not correct, you can have other problems like not reaching a hardness value that is required, or even cracks that can appear during the process. And these are some very common failures that are interesting to detect using different techniques. Regarding that, one of the problems linked to this detection is that in all the industries that heat treatments are applied, we need some inspection of these workpieces, and the usual way of doing is to use a destructive testing. So you have to, we're going to see it later, but you have to destruct some components in order to measure what's happening inside. And this has several problems linked to that. If it's a batch manufacturing, and this is an offline testing method, usually when you perform these destructive tests, it can bring some material waste in batch. So you have several components that are lost. And also, if this is a unitary manufacturing process, you need a lot of time and material to reach a proper recipe for your manufacturing process. So it brings also some material waste because of this destructive testing. So the goal with this idea here is to develop an inline non-destructive test or inspection technique in order to reduce this waste associated with the inspection of the material. And the idea here is to have it inline or in real time, so we are able to correct the manufacturing processes during the process itself, and we don't need to destroy a full batch of material. So as we said, the usual way of performing these hardness measurements is to perform destructive testing, and this is valid for any industry that uses heat treatments in their process. The main destructive test that is used is hardness measurements. For that, you need to cut the specimen that you need to analyze, and then you have to use specific equipment to measure the hardness inside the part. And in this case, for example, we are seeing a slice of a large size bolt where you can see different measurements in a cut specimen. This, of course, requires a lot of time, as we said, material waste, and also prepared personnel to do that in a laboratory. There are other techniques that are not that used in the industry, that are non-destructive testing, different inspection techniques. Here we can see 4 different examples. Maybe the ultrasonic testing is the one that is mostly used, along maybe with the eddy current. But all these methods have something in common, that in terms of measurement depth, they have some limitations. Each technique has its own characteristics, but it's something in common, that in order to perform non-destructive testing with the inspection techniques that are available in the industry, you cannot measure what's happening inside the material up to a certain part. So this is the goal that we have to achieve in this solution. So if we start with the digital twins that we are developing for the mechanical hardness inspector that we developed in IKERLAN, we are going to start speaking about digital twins, just to make sure that everyone is on board with the same idea. Digital twins, as we know them here at IKERLAN, there are many readings to the term, but for us, this is a virtual replica of the manufacturing process that uses real-time data to predict what's happening inside the part, or in the part. And the idea of using digital twins is that we can forecast the process outcome while it's happening. So we are able to detect defects that can happen in every part of the component that we are hardening, or even detect inefficient processes, that we are going to see an example later. Digital twins has to be trained from different data, and there are two main ways of training a digital twin. One of them is based on data, on experimental data mainly, and then you can use physics-based models, and you can also do a combination of both. In this case, we are training these digital twins with physics-based models because it helps us to minimize the waste associated with the development of the digital twin. This means that we don't need to perform many cuts in different manufactured components to get enough experimental data to train it. So we are able to perform all this analysis without wasting any material. And in our case, we are going to see it later, but we are training our digital twins from data obtained from a finite element model, where we are able to replicate the manufacturing process. So the idea of these digital twins is to move from a local and post-process measurement technique to a global. And when we say global, we mean that you can analyze any point of the component that you are heat treating, and we can also analyze real-time data. So we are able to see what's happening inside during the process and not only after it has been finished. So if we move to the solution that we have developed in the ZDZW project, its name, I said it before, but its name is Mechanical Hardness Inspector, MHI. And this non-destructive inspection technique is based, as we said, on digital twins. The idea of this solution is to have an inline mechanical hardness estimation in the induction processes. And what we are using is machine sensor measurements in real time. So we are able to estimate what's happening inside of the part using the digital twin that we are developing. And this during process time is quite important for the solution. With this solution, we are able to perform an automatic unitary inspection. This means that even if we are producing in batch all the in this case bolts that we are manufacturing, but it can be applied to any other component, we are able to see what's happening in every component that we produce. So from one to the next one, we are able to modify the process parameters if we check that something is wrong, or if we detect some defects or some inefficiencies in the process. And as we said, this is an inline non-destructive inspection. It can be incorporated into the machine itself. So here, these graphs allow us to more or less explain the idea, but we are going to see it later. We have some finite element models, physics-based models for induction hardening, where we can create all this virtual data that we need for training the digital twin. And once we have this digital twin, we have some experimental data coming from the machine itself in real time, and we are able to have a real-time inspection. And the two goals that we have for this solution is to estimate the martensite formation in depth of the bolts, and with that we are able to estimate the hardness profile, and we are going to see some results later. And where can we use this mechanical hardness inspector? Here you can see some sectors that apply heat treatments in their manufacturing processes. But as I said, in many sectors and many components, you can find heat treatments because it's a basic manufacturing process in many industries. Wind energy are some important sectors for applying these hardening and tempering solutions. So if we go step by step through the training process of a digital twin, here you can see the architecture that we are using to train our digital twin. First, of course, we need to start with the data generation, and we have to start with a finite element model that replicates our manufacturing process as it is. So we are able to see what's happening in the process that is already being applied in the pilot or in any other case. Then we have to identify the key process variables, and with this model we are able to modify them accordingly so that we can generate a virtual data set that can be used for training the digital twin. Of course, we have a training stage where we have to train and then validate our digital twin. In this case, we are using artificial neural networks, but other techniques can be used also to train these digital twins. And then finally, we come to the usage of the digital twin as an entity inspection technique. And here, what we are doing is putting together the digital twin and real-time data from the physical system or from the machine itself. And this opens the possibility, once we know the Hardness case that we have achieved in a specific manufacturing process, it opens the way for closed-loop process control, which is very interesting for future lines. So if we go step by step through the process, first we have to start with the finite element model preparation. In this case, we are already looking at the pilot use case. If you remember, it's about large size bolts from Eureka. In this case, we need some information, of course, from the process itself. We need the initial recipe and also the geometry of the bolt or the component itself and the inductor system that we are using. And in this specific case, we also have some induction heating steps and different movements. So we are able to replicate that using our finite element model. Here, for example, you can see that we have 4 different heating stages with some movements in between. And in red here, you can see the Hardness case depth that we are achieving. So you can see that when the process continues, you can see that we have been reaching more and more case depth. If we take a look at a specific point, for example, in this point here in the surface, and look what's happening inside, if we look at the Hardness case depth in that point, we can see that in the initial steps of the process, we don't have any Hardness case depth. It increases, as you can see here in red also, that we have more and more red in this cross section, and then in about 50 seconds or so we reach full depth, which is one of the goals that we have in this pilot. We have to harden the whole section of the components. So once we have the initial finite element model where we replicate the exact manufacturing process that we are using, we can create a virtual database. For that, we need to define, first identify the key manufacturing variables for this process, and then modify them inside some logical region from the machine. And once we develop all these simulations, we are able to create this data set. And here, for example, you can see 4 different cases, different combinations of key variables of the process. You can see the gray one is the basic manufacturing process, the original one that they are using, and we can see that changing different parameters changes the response in the case depth. And in this one, for example, we are able to reach full section just right at the end of the process. In this case, the 2 main inputs that we have been using are peak current and frequency of the different heating stages. So once we have this database, we're able to train the digital twin. In this case, we did it using MATLAB. It has a machine learning app, and this is the one that we used. And inside all the combinations that we have, of course, we have to select the best one. And once we have an equation, a digital twin that is able to replicate different cases, then we need to validate our digital twin. And for that, we used both finite element simulations, simulating different cases that were not part of the data set, and also using different inputs that were not used for the training. And for that, we are able to specify the proper validation window for the digital twin. And this mechanical hardness inspector solution, where what we have been doing there is implementing the digital twin, so it's able to automatically use the digital twin, do these predictions, and have the inspection. Here we are going to see some screenshots of the application of the app that we developed, but we are going to see a demo later, so I will go more or less fast in here. Here we have the home screen of the ZDZW application platform. And in this case, we are already inside the mechanical hardness inspector suite, where we can, for example, do the login. Once we have logged in the platform, we can go to the new stages that have appeared here, where in this case we have only 2 more screens. So in the first one, in the model loading, what we do here is to select the machine variables that we are going to use, the digital twins that we are going to use in a specific case, and define more or less what type of inspection we want to do. Once we have set everything, we click on Set Model Configuration, and we can move to the inspection screen. And in the inspection screen, we can see several things. In this side, we can see the inputs or the real-time sensor data coming from the machine. And this is the input that is used for the digital twin to do the estimation. And in this case, and on the other side, you can see the estimation from the digital twin. Here you can see that it more or less looks like the one that we showed before. So we don't have any case depth in the initial steps, then it's increasing until it reaches its maximum at certain point of the process. And from this information, we get a summary here with the 2 main goals that we had in the project, which is detecting the time to reach the hardened case depth. In this case, for example, and we already saw it before, you are able to reach the proper case depth more or less at this point of the process. So you have some seconds of the process that could be cut short for the next bolt, for example. So you are able to detect process inefficiencies because up to this point you are doing it properly, but from here on you are just losing manufacturing time. And also, if we are able to detect the maximum hardened case depth that we achieved, we are able also to see if our manufacturing recipe was correct or not. So now we are going to move to do a live demo. I'm going to try to explain everything again, but using the solution itself. Okay. I have to change screens. Give me a sec. Okay. I hope that you can see it already. Okay, so here you have the home screen that we already saw with some information about our solution. If we move to the model loading screen, here we can choose different digital twins that we have stored in our laptop. And here you have a list of all the digital twins that you can use in the different cases. For example, if you have any different component that you are hardening, or the different manufacturing processes that can be analyzed, you would have different digital twins here in a list. In this case, we are using the one for the pilot with the geometry and material that is specified here, and we are going to select this digital twin. We have already selected it, and we can choose the simulation type. In this case, we can do an offline analysis or inspection. If we have some data stored and we can upload it here, the solution will tell us the hardened case depth of this specific component. But if we choose a streaming or inline analysis, we're going to have results all the time during the manufacturing process. Here we are also able to specify the goals that we have, the specifications that we have for this part. For example, in this case, I'm going to put 3 millimeters. So this is the goal that I have, and then all the alarms and everything will be taking this value into account. And here you can see the different parameters that we are using, and this is just to check that the configuration of the hardware matches the digital twin. So once we set the model configuration, we can move to the next one. And here, if I click on run, let's say that the machine will be performing different hardening cases. And here, for example, we have the results for one of the bolts that it has manufactured. Here we have the readings of the machine, and the output value here would be the hardened case depth. We can see that, as we said, in some seconds we don't have any hardened case depth, then it increases. Since we have some movement in between, it's a step-by-step process. And we can see that some seconds before the last point of the process, we already got the maximum case depth. And probably here we can see the result. We can see the maximum reached hardened depth and also the time required to reach the goal that I have set. In this case, for example, I said 3 millimeters, so 26 seconds would be enough because the value is around here. Okay. And here we are able to save the data into a file. But if you have been watching, there are some results here already. So we have this automatic downloading of the inspection. So we have all the data stored. So this is more or less what our application or our solution is able to do. Now I will try to go back to the previous screen. Yeah. Okay, so this brings us to the end of the webinar. I just wanted to give you some details of the current research that we are performing. We have two main lines of research in our team. We are doing new simulation models for more complex geometries. In this case, we have worked with a pilot with some bolts, but we are already working on different more complex geometries like gears, camshafts, and other types of complex geometries. And we are also working on developing digital twins for different manufacturing processes. As we said, we are working with induction and laser technologies, and right now we are focusing on laser-based processing in general, specifically in welding and heat treatments, and also in more traditional welding. And we are developing digital twins for that, similar to the one that we have been showing today. And to conclude this webinar a little bit, we have seen an inline non-destructive inspection technique that has some advantages when compared to other non-destructive techniques that we have seen, mainly focused on the inline solution, and also that we are able to see what's happening in the full part instead of a local assessment. As we said, the solution enables a real-time process monitoring, and this is very helpful for future developments on closed-loop control. And here we have demonstrated our solution in induction heat treatments, and we have been able to highlight the potential in various industrial applications as the ones that we saw for more complex geometries. And in conclusion, I would like to give a special importance to the expertise that we have in the simulation of manufacturing processes here at IKERLAN. And with that, it's important to know that we are able to increase efficiency, reduce processing time, waste, because we're able to evaluate different aspects of the manufacturing process, from the control point of view, from the inspection digital twin point of view, and also a more traditional point of view based on regular simulations and experiments. And with that, my presentation ends here. I don't know if we have some time for questions, or maybe somewhere from the audience has any questions.
Yes.
Hi, Mayalen, can you hear me?
Yeah, Pablo.
Okay, good. So I just in case anyone from the audience has any questions, I have a few of them, so maybe we can give them. I'll just ask them, and so we can give them some time to write them down in the Q&A session. So you were mentioning that the solution is capable to be used in any industry which uses heat treatments. I mean, is it can we say it is very generalistic in that aspect that you can use it basically in any kind of industry that uses that kind of treatment?
Yeah, I would say that the solution itself is more or less generalistic to any component, but we need to train specific digital twins for the different components, because we have to take into account the machine that they are using, the geometry recipes that they are using. So we would have to, following this methodology, we would have to train a new digital twin specific for this case. But the method itself and the application is valid for any case, and it can connect to any hardware or machine that they are using.
Okay. Okay, thank you. That was the point I was trying to get. So you were apart from that, you were mentioning that you used artificial neural networks. What was the thing or the characteristics that made you go for an artificial neural network and not any other type of neural networks?
Yeah, there are many machine learning techniques that you can use to train these kinds of digital twins. In this case, the artificial neural networks were fast enough to train because with the data that we had. But if you have more complex data, maybe you have to move to other techniques. In this case, our data set was, let's say, simple enough, so you can use artificial neural networks with the regular training.
Okay. That's also a very good point. And so in the end, it's just the simplicity of the process that you were involved with, right?
Yeah.
Okay. And finally, from my side, which were the biggest issues that you have been facing in order well, since the start until the end of the solution development and deployment? What were the biggest challenges that you had to overcome?
Okay. In this case, I would like to remark that the induction heat treatments are a very complex manufacturing process, because it involves different physical aspects. It's highly multiphasic. So developing all the simulation models that can be used to train a digital twin, this has been a great challenge. And also it's important, especially if we have these kinds of multiphasic analysis, to have models or to develop models that run fast enough. So you are able to create this virtual data set. So I would say that this was the big challenge, developing the models and making them fast enough so you are able to use them in logical time. These simulations run in a few hours, and it's not typical for these types of simulations. It's usually a day or more, even a week of simulation. So we were able to reduce the computational time greatly, and this was the biggest challenge, I would say.
Okay, thank you. Great job then. And with that, all my questions are done. I don't have any more questions, and I don't see any other question from the audience. So I think we can close this right now. So thank you, Mayalen. It was a very insightful webinar, really interesting. I hope the audience enjoyed it as well. And I would like to just have a brief moment to thank everyone who has been assisting to these webinars. This was the last one of the ZDZW webinar series. So we hope this series has been insightful. You've got great knowledge from us. And for any further questions or any further information, you can always look up for the website of the project, and also see the past webinars as well as this one in the YouTube channel. And you can formulate any questions that you might find interesting. So, without further ado, thank you very much, Mayalen and all the crew from IKERLAN, and I guess we'll see you around next time.
Yeah, that's it. Thank you. Bye.
Thank you. Goodbye.